So in this third of 3 videos, I'm going to start on the PowerPoint slide that says molecular polarity. It's the first one after geometry and shape, which is the last video. If you haven't watched the shape and geometry video, it's going to be a large part of what we do on the first exam. So make sure you can do that. And ask me questions in class Tuesday, and ask me class by email, and I'll try to answer them as best I can. Be aware that on holiday this week I am going away with my family, and so I'm very much limited in what I can answer. I'll try my best. That's the best I can offer. Unfortunately, neither of us would prefer that I'm standing here on a Thursday afternoon making videos of the lectures you wish you could have heard in person live. I'm not enjoying this anymore, and you are. But anyway, here we are. We have to do this. You have to watch these. Hopefully another 20 minutes or so, and then we'll be done chapter 3. So, what I want to talk about is polarity. Now, what am I talking about? Well, so we've agreed, remember we've now agreed to, for the rest of this chapter, as I said at the beginning of the shape and geometry video, the second one, I said let's just, for the rest of this chapter, talk about bonding as if it's always covalent. As if when 2 electrons are in the same place, they're sharing those 2 electrons in a bond. It's a terribly simplified view of the world. We know that when magnesium and chlorine come into contact, the chlorine steals the electron from the magnesium. It makes MgCl2, Mg plus 2, the metal cation, Cl minus 1, the non-metal anion. It's an ionic bond, but we're going to pretend it's all covalent just for now to have a simplified view of the world. So why am I telling you that? So what I want you to know is, if we're pretending that everything is about sharing of electrons, we're not, however, pretending that they share equally, right? It's not like if I had magnesium and chlorine in a bond, I would imagine that the 2 electrons would be shared between the magnesium and chlorine. In fact, I know intellectually that the electron's gone, it's over with the chlorine, making chloride. But if we call everything covalent, we know that bonds are shared, but are they shared equally? And of course they're not. And this leads to polar bonds, bonds where the electrons are closer to one atom than the other, and so one end is negative and one end is positive. Or if, in this case, since they're covalent, not totally negative or totally positive, but what we call, watch finger flexation, partially positive or partially negative. So we can talk about polarity leading to asymmetric bonds, bonds where the electrons are closer to one atom than the other in the bond. And so people realized that this was a reality they had to confront, and a very wise man, whose name could come up in every class I give, which is Linus Pauling, actually codified a scale in which he could talk about how much a particular atom wanted to pull electrons toward it. We already know that chlorine has a greater pull on electrons than magnesium, because chlorine's a non-metal, so it wants the electrons. Magnesium's a metal and doesn't want them at all. So we know that chlorine has a greater pull on electrons. So Pauling actually devised a scale in which he had all the atoms compete against each other. And he came up with a scale. Now it's a relative scale. He made up the units. It's not like it's in units of joules or calories or I don't know what, and some unit of energy, although it could have been. But this is an arbitrary scale, relative speaking. So he came up with a scale of the relative pull on a pair of electrons in a covalent bond between any 2 electrons. And I've always believed, although I've never read why he came up with it, that because Linus Pauling was at California, Berkeley, and he was a teacher, not like me, but because he was unbelievable, but same idea as me. Because he was a teacher, he had any kind of scale he could come up with. So as a teacher, what did he come up with? 4.0 scale, right? And 4.0 is A+, right? So he came up with a 4.0 scale. It's a relative scale. It's a relative scale of the pull on a pair of electrons in a covalent bond. And he had a term for this, right? And the term he came up with was electronegativity. Electronegativity is, in fact, by definition, and you'll see it on the second slide, the relative pull on a pair of electrons. Think about the words I'm saying. The relative, no units, relative pull on a pair of electrons in a covalent bond. So if you have the PowerPoint out while you're watching this, which I would recommend, you could look down at the slide that's got the word electronegativity at the top in red, and it does say, I assume, the relative ability of an atom to pull a pair of electrons towards itself in a covalent bond. It's the relative pull on a pair of electrons in a covalent bond. It's as if I'm saying it 4 times because I'm going to ask you, what's the term for the relative pull on a pair of electrons in a covalent bond? You're going to answer electronegativity on the first exam a week from next Thursday. So, and you can see below it his 4.0 scale. Remember that we said that the guys in group 7, the halogens, what distinguishes them is that they're so toxic. And the reason they're so toxic is they're 1 electron short. Imagine being 1 short of being a noble gas, right? So if you're fluorine, neon's got 1 more electron, perfect. If you're chlorine, argon's next door. If you're bromine, krypton's next door. Iodine, xenon's next door. 1 more electron, you want 1 more electron. And the guy that's the worst about this, the most toxic one, back when we talked about halogens, remember I said no one does any chemistry with fluorine, it's so dangerous. And so fluorine is the A-star student. Fluorine gets a 4.0. No matter what you bond with fluorine, fluorine is more electronegative. It pulls the electrons towards it no matter who it binds with. Even if fluorine were to make a fluorine-chlorine bond, the electrons would be pulled from chlorine towards fluorine. It's more electronegative. Oxygen's more electronegative than nitrogen. Nitrogen more than carbon. Carbon more than boron. What you notice is that everything gets higher in number as you get towards fluorine. So if someone asks you, what's more electronegative, sulfur or oxygen, you look at them and you say, well, oxygen's closer to fluorine, so it's going to be oxygen, right? What's more electronegative, selenium or sulfur? Well, sulfur's closer to fluorine. Whoever's closer to fluorine is more electronegative. What's more electronegative, iodine or bromine? Well, I don't need the scale to tell me bromine's closer to fluorine. And whoever's closest to fluorine is the most electronegative. All right, so that's how the 4.0 scale works. I'm not going to give you a 4.0, Pauling electronegativity scale because I don't care if you know what the numerical value of carbon's electronegativity. You can see that it's 2.5. I cheated and looked down. Who memorizes the electronegativities? But I would like you to be able to answer the question, who's more electronegative, phosphorus or silicon? Because you would just look down and say, well, phosphorus is closer to fluorine. It's more electronegative. Fluorine is the perfect 4.0. Carbon, you'll notice, got a 2.5. It's about a C student. See the joke there? Anyway, so that's electronegativity. And why do we care? Why do we care about electronegativity in the 4.0 scale? Because we already know that magnesium gives its electrons to chlorine. You'll notice that magnesium's 1.3 and chlorine's 3.0. Chlorine is much more electronegative, and that's how you say it. Chlorine is much more electronegative than magnesium, right? Meaning it pulls the electrons away from magnesium, the metal. Why do we care? Who gives a darn? Well, it turns out that the reason things stick together, remember our discussion of ionic bonding, is they have some force. And we've talked about 2 forces. within atoms, within molecules. So why is sodium chloride a salt? Well, it's a metal and a non-metal, and the electron transfers. You'll notice that sodium is 0.9 and chlorine is 3.0. Lots of difference in electronegativity. And then these two ions stick together. That's the force that causes the bond. Why does carbon and oxygen form a covalent bond? Because they're nonmetals. They both want electrons, so they share them. That's covalent bonding, right? CH4 is about 4 hydrogens. Electronegativity, you'll notice 2.1. Sharing with carbon. Carbon's slightly more electronegative than hydrogen. So we can talk about, even in covalent bonding, we can talk about polar bonds, right? We can say, well, we saw in the last PowerPoint carbon forming a double bond with oxygen, and it's covalent, so they share the electrons, but we know that they don't share them equally. The electrons are actually pulled towards the oxygen because its electronegativity is 3.5 and carbon's 2.5. You'll notice I'm cheating and looking down at my laptop, which is right down here in front of me. You don't have to memorize the numbers, but oxygen's closer to fluorine, so it must be more electronegative. So why do we care? Well, here's why we care. In chapter 2, we talked about the atom. In chapter 3 so far, we've talked about 3 types of bonding. We've talked about ionic bonding, covalent bonding, and briefly metal bonding. Now I want to tell you about 3 types of forces. What's the difference? Well, bonding happens in a molecule. It is covalent bonding that makes H2O, H2O, and it's always H2O. It's not any other combination, right? A molecule, methane is CH4, ammonia is NH3. These ratios of atoms are fixed. But here's the question we're going to answer. Why is methane a gas, but ammonia a liquid? Water's got not only a liquid, but its boiling point is really high, 100 Celsius. Can you imagine? 100 Celsius. You have to get a Bunsen burner out to get these waters to boil, but you know, water is tetrahedron, methane is tetrahedron. They're both at 109.5. One has 4 bonds to 4 hydrogens, that's the carbon. One has 2 bonds and 2 lone pairs. Why is one a methane? I think methane boils at 16 Kelvin, which is like minus what? 257 Celsius? And water boils at 100 Celsius. They're like 300 degrees apart. Why? Or more than 300 degrees apart. Why are their boiling points so different? So we're now talking about 2 molecules, right? So here's an ammonia and here's a water. If they came in the same environment, would these 2 atoms stick together enough to form a liquid? We're talking about between molecules, right? So interscholastic sports is between 2 schools, right? So a bond is intra, it's within the molecule. Now we're talking about intermolecular forces. It's the last idea in chapter 3. And it's all about polarity, right? So why is hydrochloric acid a liquid? Well, hydrochloric acid is hydrogen and chlorine. Chlorine is much more electronegative. It pulls the electron density towards it. Let's go to our scrubbed up whiteboard, and draw a chlorine and hydrogen, right? So how do we notate that this is not a equally shared covalent bond? Well, what we can say is that the electrons are being dragged that way, right? Now, science puts a little plus sign on the back. Notice it's got a plus sign. And so there are the electrons. Electrons going that way, right? Because chlorine's more electronegative. That's an E- up there. What's another way to indicate this? Remember I said that these are all covalent bonds, especially here, 2 nonmetals, not all covalently bound, But what I want to indicate is that it's very polar, that there is partial negative charge here on the chlorine, partial positive charge on the hydrogen, because the electrons are actually, this covalent bond, these two electrons are actually over here. So what I can do is I can write delta plus. And I can write delta, it's a Greek letter, minus. So what that says is partially negative, partially positive. It's a polar molecule. And it's therefore, if you look at it, look, here's the molecule. It's got a negative end and a positive end. All right, it's got a negative end and a positive end. And because of that, HCl, like if two HCl's came near each other, right? So you have, here's an HCl, it's got a negative end and a positive end. Here's another HCl, negative end, positive end, right? The two negative ends come near each other. You've done this with magnets in your past. The two negatives would hate each other, the positive would love each other, and they stick together and they form a liquid. It's an intermolecular force. HCl in blue, HCl in red. It's an intermolecular force, and it's true because while it's covalent, it's a covalent molecule, it's a polar covalent molecule, so each one of these is like a bar magnet, right? And that's the intermolecular forces. Because this has two poles, the negative end and the positive end, we call it di, meaning two. Remember, diatomic, two atoms. This is dipole forces. The force between these two HCl's, because it's polar molecule, is called a dipole force. Here's a molecule with two poles. Here's a molecule with two poles. It's got a dipole force. We see this all over the place, right? Remember we said, we looked at that molecule last video. We said, oh, here's this molecule. This is actually called formaldehyde. Formaldehyde's the stuff they put snakes in to preserve them for 500 years at the museum, right? Or whatever, a dinosaur or something. You can preserve animals in this formaldehyde. But what do we know about this molecule? Well, we can see that it's got three things coming off it. It's worth remembering that this is therefore a planar triangular geometry. And it has no lone pair, so the shape is the same for the central atom. It's planar and triangular. 120 degrees. I'll write that in. 120 degrees. So, there it is. 120 degrees all around it, planar, triangular, but not symmetric. What do I mean? Well, oxygen is really electronegative. So it's pulling the electrons towards it. Right? The electrons are being pulled north. Remember that arrow indicating where the electrons are headed? Plus sign at the bottom. Or we could write delta minus and delta plus. But what else do we know? Well, we noticed, because we looked at the Pauling scale, that the hydrogen would give up electron density towards carbon. Carbon's more electronegative. So that's headed that way. Right? So that's positive also. Delta plus. So this overall molecule has a polarity. Notice, right, the electron density. This side is, whoa, this side has got all the negativity, and this side's got all the positive. It is a polar molecule. How can I indicate that? There it is, a polar molecule. It's not symmetric. It's got two poles. It's got a negative end at the top and a positive end. So like the HCl, because it's polar, it's got two poles. It's dipole. And you're not surprised to learn that because it's polar, and therefore two formaldehydes would come near each other and arrange themselves. And then the next one would stick on, and the next one would stick on, right? That formaldehyde, like HCl, is a liquid, right? Because it's got a, ready, intermolecular force. a dipole force. Why dipole? Because it's a polar molecule. All you have to know is it's a non-symmetric molecule. So, polar bonds and polar molecules, right? So that's what we're talking about here. Polar bonds can exist, and they usually mean a polar molecule. What's the extreme? What's this one? Here's the extreme. Tetrahedral geometry, but a bent or angular shape. Right? There it is, 109.5. It's water. And the oxygen's really electronegative, so it's pulling the electrons from the hydrogen towards it. Right? This is positive. This is positive. There's, look, 4 electrons. Look at all the negativity there. This molecule is incredibly polar. All the electrons are up there. Negative, go away. Positive down here, right? Water's unbelievably polar. There's water, right? Water's really polar. And because it's so polar, because the dipole forces are so strong, it's not only a liquid, but it's a high boiling point liquid, and anyone will tell you who shoveled snow all day, like I did today, that it's not far from being a solid at room temperature. You only have to go down to 32 Fahrenheit, 0 degrees Celsius, to get to the the melting point of water, the freezing point of water being the same thing as the melting point. So, polar bonds, very polar molecule. Remember again, geometry and shape. Geometry is tetrahedron for water. Shape is bent or angular. Still 109.5. I'm going to ask you about that geometry and shape stuff, so don't forget that. Really work on it until it makes sense. So, does geometry always mean, does polar bonds always mean polar molecules? No. So there's an example on the same page. I'll tell you what I'm doing, just so you know. I'm looking at the same PowerPoint you are. There's an example up here. We know that methane is tetrahedron. All the hydrogens around it are perfectly symmetric. So whether the electrons are being pulled towards the hydrogen or towards the carbon, they're symmetric in all 3 directions. 4 directions, whatever. 3 dimensions. It's a perfectly symmetric molecule. And because of that, there's no polarity. It's not a dipole molecule. It has no polarity. So, not surprisingly, if one CH4 came near another CH4, they just bounce off each other. They have no polar negative end or positive end. It'd be like 2 nails just knocking into each other and bouncing up. They're not polar. Why would they stick together? 2 Legos just sitting in a bag together. They don't have any force of attraction or repulsion. Neither does this, because it's not symmetric, or because it is symmetric. And you're not surprised to hear that this boils at like 16 Kelvin. That's almost absolute zero. But look at this, and same idea. Here's another tetrahedron with carbon in the middle. We know which way the bonds are going. All these chlorines are pulling electrons off the carbon. Carbon's being stripped of all 4 of its outer shell electrons. But the chlorines are totally symmetric around it, right? Wouldn't matter if they were hydrogens around the central carbon or chlorines around the central carbon. This symmetry is that you wouldn't know which ends up, down, left, right. It's totally symmetric molecule. Imagine for a second that, I mean, it doesn't matter whether these spheres are hydrogens or chlorines, right? If they pulled all these are white ones are now chlorines. Play along. They're pulling all the electrons towards the chlorines. Carbon's losing all its electrons, but there's no polarity here, right? There's no north pole and south pole. There's no plus or minus. Once again, it's totally symmetric, right? So once again, a gas at room temperature, right? But create some asymmetry. Now I'm going to draw, remember, we've got methane. This is called tetrachloromethane, 4 chlorines. And so let's create one with 2 chlorines. All right, so this is called dichloromethane. Two chlorines, dichloromethane. Now we've got some real symmetry, or we've got some real asymmetry. Those electrons are being pulled towards the carbon. Those are pulling the electrons down. And so now we've got a totally polar molecule. Now we've got water again, right? A negative end and a positive end, 2 poles, dipole forces. Because it's asymmetric, it's very polar. And you know, in this laboratory, in this room, we have dichloromethane. It's a liquid at room temperature. Its boiling point isn't as high as water, but it's like 65 Celsius. It's pretty high. So by having an asymmetric molecule, you have 2 poles, dipole forces. And so you have a polar molecule. So that's important. So polar bonds, electronegativity, Pauling scale, but polar bonds don't necessarily mean a polar molecule, right? We see back there, somewhere back there, we see, just as it is on the on the PowerPoint, polar bonds, a nonpolar molecule. Polar bonds, nonpolar molecule. But polar bonds, very polar molecule. And the boiling point here is 65 Celsius. Here it's like minus 200 Celsius. And here it's minus 257 Celsius. Right? So very different boiling points if it's polar versus nonpolar. And that's polar bonds and polar molecules. And that leads us to the 3 types of forces. We've talked about one. We've talked about dipole forces. An asymmetric molecule, which has therefore a negative and positive end. Basically anything without symmetry is polar, and so it's got dipole forces by definition. Now, there's an extreme of dipole forces. It's actually such an extreme that it gets its own name, but it's really polar molecules. So here's our friend water. Excuse me, there's water. Water has such polarity, because oxygen is so electronegative. And the other example of this is nitrogen. When nitrogen or hydrogen have nitrogen or oxygen have a hydrogen attached, it's not just polar, it's megapolar, right? Nitrogen and oxygen are up there next to fluorine. They're really hard and small, and they pull electrons towards them, and they're really super negative, and they make a really strong polar bond with hydrogen. So anytime you have an O with an H attached, or an N with an H attached, either of those, O with an H, N with an H, you're going to have polarity. Just going to. And it's going to be so polar that it gets its own name. And that name is actually, it's a force. It's an intermolecular force, but it's so strong that it's become known as a bond. It's known as hydrogen bonding. So it involves hydrogen, but only when the hydrogen's bound either to a nitrogen or an oxygen. When the hydrogen's bound to an oxygen or nitrogen, it's called hydrogen bonding. And why do we care? Why do we give this little nitrogen or oxygen bound to hydrogen a special category? And the reason is that biology counts on it. It counts on the hydrogen bonding of water, right? You're 70% water. I'm pointing at you and me. I'm 70% water. But not only is water hydrogen bonding, water is actually an oxygen with 2 H's attached. It hydrogen bonds in 2 different places. But your DNA is full of hydrogen bonding. It's what holds your DNA together, actually. Your proteins are full of hydrogen bonding. It's why your proteins fold the way they do. All stuff we're going to talk about in April or May if the snow ever stops. So that's important too. You need to know that N's and O's with an H attached, only that is hydrogen bonding. And now, the last thing is called dispersion forces. Really, all the dispersion forces says is when you have a symmetric molecule, like methane, it doesn't have many electrons to move around. Methane doesn't. But when you have 4 chlorines around, the chlorines have lots more electrons, and they could sort of slosh around. So they could, for whatever reason, slosh around. It's the sloshing effect. The more electrons, the more sloshing. So if you have CH4, you have very few electrons, very little sloshing, very little ability to create an asymmetry. If you had carbon with 4 chlorines, all the chlorines have electrons, they can slosh around. They can become temporarily asymmetric, and that's called, this weak force. There's a weak force. And remember I said the CCl4 is slightly higher in boiling point. It's like minus 200 instead of minus 257. So, a very weak force. But it comes into play in your life. So methane's definitely a gas. And 2 carbons is called ethane, definitely a gas. 3 carbons in a string, propane, definitely a gas. Keep going. Butane, like the stuff in the lighters. It's a gas, but if you put it under pressure inside those lighters, it liquefies. Methane wouldn't do that. But butane's got more electrons, so the more electrons, the more temporary dipoles you can make, sloshing around of electrons. When you get up to 8 carbons, it actually has so many electrons that they could slosh around on the molecule and form an asymmetric molecule at any one point, and actually form this temporary dipole and be a liquid. So the bottom line is symmetric molecules only have dispersion forces. We call them dispersion. In high school, you may have called them van der Waals or London dispersion. We'll call them dispersion because the text does. But be aware that if you hear van der Waals, it's basically what we're talking about here. So very weak force, but it has to do with the number of electrons. All right, so you get up to 8 electrons, or 8 carbons. It's called octane, oct being 8 like an octagon. So octane, and we're going to do carbon chemistry later, but octane's a liquid because it's got so many electrons. In fact, octane is commonly referred to as gasoline, petrol. Another example of dispersion forces. You have diatomic fluorine. Each one has 9 electrons. Not much sloshing, right? F2. It's a gas at room temperature. Boils very low boiling point. Chlorine has more electrons, Cl2. Because it can slosh around a little more, its boiling point is higher, still the gas at room temperature. Bromine has another shell and more electrons, so we can slosh around more. So that means that bromine has so many electrons that it can form this temporary dipole. It can slosh the electrons around. So bromine's a liquid at room temperature, very, very low boiling point, right? You swirl bromine around, it makes this dark blood red gas. It's really toxic. Don't do it. Iodine, well, iodine's got another shell of electrons. So many electrons slosh around that iodine will form a temporary dipole so strong that it forms a solid at room temperature. And this is an example of dispersion forces. Dispersion forces is symmetric molecules, F2, Br2, I2. Symmetric molecules that can temporarily be asymmetric because they have enough electrons to slosh them around. And that's the weakest force. It's very weak. It's nothing compared to dipole forces. And the extreme of dipoles, the bionic dipoles, is hydrogen bonds, which is an N or an O with an F attached. So here we are. I'm on the last of 3 videos related to chapter 3. There's really nothing more to talk about other than that you need to go watch these videos again. And if I haven't done a good job, watch someone else talk about shape and geometry. By the way, you don't need to know about anything I didn't say. So you don't need to know about trigonal bipyramid or octahedral, L-shaped and all that. Just the ones I said. Know about those shapes and geometries, bond angles. That's the second video. You need to know about ionic and covalent. In a sense, what I've shown you is 3 videos. The first one is 3 types of bonding: ionic, covalent, metal bonding. The second one's shape and geometry. And knowing shape and geometry, now we can do the third thing, which is 3 forces: hydrogen bonding, dispersion forces, dipole forces, all based on polar molecules, based on polar bonds, based on Pauling's electronegativity scale. So that's the rest of chapter 3. I would have done it in class, but that didn't happen. So now you've seen these 3 videos, you're responsible for them, even if you haven't seen what I'm saying, in which case I'm not talking to you. But you're responsible for them, you need to learn them. Watch them again, watch them 2 or 3 times, and then write me a question, and I'll try to answer as best I can within my limited scope, because I'm on holiday and I have to do that. And when we come back, unfortunately, on Tuesday, we're going to talk about chapter 4. You'll notice the next slide on PowerPoint is atoms, molecules, moles. And that's what I'm going to talk about Tuesday, and we'll be okay for the first test. So, if you're watching this during your holiday, sorry to ruin your holiday, but homework is due Tuesday when we get back, and these videos, these topics, they're all part of that homework, part of your responsibility. And so we're all adjusting to the weather, and I hope this was valuable. I hope this solved your concerns and made this all a doable project. And I'm wishing us all the best of luck.